Okay, so let's come back. So this kind of assessment for probability distribution will basically give you a graph already, but you can also use a method called relative heights. Okay, or basically graph drawing directly. You first draw this. You ask people what is the most likely event. Okay, and so you ask for estimation of the how likely that is. So it's a single probability. You can either ask that directly or indirectly. After you have this height, After you have this height, then you ask for the second highest height, but you don't ask directly how high that is. You ask for a relative probability or relative chance of happening. So maybe that's gonna be this one. So for example, this is approximately 0.8 of the red line, I guess. Okay. Then you do that, one by one. Then you will have, this. Basically, you will have a approximation of a distribution. This will lead you to give a curve like this. This is what it means by fit a curve. Okay? And after you fit a curve, you will have the PDF. PDF. After you have the PDF, you will be okay. It's the same thing as here. Okay? So that means by relative height. I guess some people are better, you ask them this way, and some people it might be better if you ask them this way. Okay? Yeah. Oh, one thing about relative height. You don't need to really get a specific probability. Okay, so for example, this height can be 10. The height of this red line can be 10, can also be 20. As long as the relative height of all these are, the ratio are the same, that's fine. Because we're gonna normalize the ratio like this. So for example, in this one, the highest height is 10. The second highest is 8, 6, and so on. These add up to 36, but that's not 1 or 100, right? So I will normalize that by dividing everything by 36. So here, 2 is divided by 36, 10 is divided by 36, so that together these will add up to 1. Okay? And after you do either the direct method, indirect method, or the just use word as a descriptive probability measurement elicitation method. At the end, you want to do some consistency and coherence check. I already talked about this, but basically here the example the textbook gave is whether PA and P not A, or actually in this class I was using complement. So this equals equal to 1, or PA and the decision probability is going to come. Oh, and this is suppose it's this case. So for example, if you're rolling a dice, there's only 6 different possibilities, right? Or if this case you're talking about the company or stock market, a stock index is either to go up or down or stay constant. There's only 3 possibilities. So these all three possibility need to add up to 1. So you check for this kind of consistency and coherence to make sure that your assessment is not too far away. Okay? Okay. And after you do the assessment, or if you observe someone do the assessment along the way for a long time of history, how do you tell whether this guy is good at the assessment or not? Okay. The example that you face every day, or I guess sort of every day, at least when I was a kid, I watched that every day, the weather forecast, right? Weather forecast, there's a weather broadcaster, or what's that called, weather anchor. He or she will tell you the probability that tomorrow will rain, right? And you observe that information every day, and how do you assess whether this person in the long run is a good assessment, probability assessment maker or not? Okay, the way to do this is it's called calibration. Okay, so what it means is this. So if in the past, this is you now, in the past there may be 10 events. In these 10 events, you all assess the probability of event A happens with 20%. If it turns out that out of these 10 events, this event A actually happened twice, so out of 10 times, that's also 0.2, right? If these two equal to each other, that's called perfectly calibrated. Okay? Do people understand what I'm saying? Okay, so this is just one probability. You might, so for a weather broadcaster, he or she may make a prediction like what is the probability that you will rain? So today is 10%. Okay, suppose they only make prediction on 0%, 10%, 20%, all the way up to 100%. There are still 11 different predictions, types of prediction, right? And suppose in the past 10 years, there are more than 3,000 days. And in these 3,000 days, every day there is a raining probability measurement. And it's either gonna be 0%, 10%, or to 20 all the way up to 100%. And you can draw the estimated probability on the x-axis, and then the y-horizon you can put the point on the actual average probability in those events. So in plain English is you collect all the past weather forecast that says tomorrow's the raining probability is gonna be 10%, for example, and then you look at those day after that day, what is the average chance that you will actually rain? If it is actually 11%, then the point in 10% will be around here, maybe. So it's above the 45-degree line. If it is perfectly calibrated, that means in the past you estimated it as 10%, actual happened with 10%, then it's gonna be exactly along the 45-degree line, because the estimated and the predicted, what actually happened will be the same. Understand? Questions? No? So that's how you draw the line. Okay, so here the the example here gives two different possibilities. One is this curve. One is this curve. So red curve means the probability are too low. You estimate it as 20%, but what actually happened is 40%, for example. And the blue line is too high. So you estimate it as 40%, but what actually happened is around 20%. So both lines are off calibration, are not perfectly calibrated. Only the 45-degree line is perfectly calibrated. Okay. But calibration, so wait, this is actually a pretty important, concept. Do people really understand what is calibration now? Yes? No? Yes?
How do you estimate the perfect calibration?
How do you estimate what?
The perfect calibration.
The perfect one is not estimated. I'm just saying if this red line or the blue line happens to lies on the 45-degree line, that's called perfect calibrated. Because your estimated always equal to the actual what actually happened. Okay. For example, maybe this example will give it a clear view. So if there's a line looks like this, so it is perfectly calibrated in this range, but probability are too high in this range. So this is still possible. So you make very good judgment when the probability is lower than 50%. But your judgment above 50%, you always make it too high, too probable. Understood? Okay. Okay, but calibration is actually not everything. Calibration can be misleading sometimes. Okay. A similar example is this. I guess most of you should heard of this. So a broken clock can be correct twice a day, right? You understand what I'm saying? And similarly, if a broadcaster, if he or she knows that on average in Taipei, the average raining possibility in the whole year is probably like 60% something. Okay. If this guy just keep making the same prediction, 60%, 60%, 60% every day for the whole year, then the calibration will be just 1 point because all his estimation is 60%. And because over a year is roughly about 60%, so his calibration is quite correct, right? But that's not useful, right? Just like the clock is always correct twice a day, is not very useful clock. Okay, so I keep making the same prediction. I keep pointing my, finger at the same number in the clock. It doesn't really help. It's called finger or arm. Arm, I think. Okay, sorry. Understood the idea? So, for example, this is actually the actual weather forecast in, I believe, Singapore. Okay, in a week, from actually 5 days in a week, I guess. So every day the chance of raining is basically 60% or so. If this broadcaster keep making the 60% every day, that's not really useful. Is that clear? Okay, so how do we sort of account for that and make an adjustment? We usually use something called the Brier Score, but the idea is actually quite simple. Okay, the idea is this. The reason why keep making a 60% prediction is not useful is because is not actually always happen with 60%. It is more like sometimes in the summer, the raining percentage probability is more likely to be 80%, so it's higher. But in the winter, it's probably 40%. It's lower. So you look at the whole year, true, that's actually on average 60%. But you don't want that information. So we want to make this kind of deviation from mean to be something accounted for. Okay, and the more the actual event deviate from what's actually happening, we want the punishment to be more severe. So what it's actually used is this score is actually quite easy. So this x is equal to 1 if I wrote it here, sorry. So x is equal to 0 if the event does not happen. X equal to 1 if the event occurs. Okay, and P is the estimated probability. So in the weather forecast example is, I look at the past 10 days. 10 days ago, what is the date? So 18, right? Okay, so 18 all the way to today. Okay. I have 10 weather forecasts in the past, right? What I do is every forecast is associated with the actual event. So, for example, today's forecast is associated with tomorrow's weather. Today's forecast about tomorrow's weather and tomorrow's weather are a pair, right? So if the estimated probability that for today, the estimation, I just checked it, the raining probability is 10%. And I look out, it actually didn't rain, right? So x equal to 0 because the event doesn't happen. So here it is 0 minus 10% to the power of 2 and 1 minus that. That's for one day. And you can do that for many days. And suppose the weather forecast say is 10%, then I look out, now it's raining, then this number is going to be 1. And if it is 1, then this number will be much bigger, right? Before it's a 10% time itself is about 1%. Now it's a 90% time itself is about 81%. Okay? And then you get the idea, right? So there's basically this is a punishment. So, and you average out in the past 10 days, this Brier score. That's the performance that we actually want to see. In that case, if you make, so in this case, there's a trade-off here. You make a very precise prediction. For example, you make a prediction on a secondly base. That's possible, right? You make a prediction about outside weather on a second base. I estimated the next second's raining probability. Then you will have a lot of predictions. Okay, 1 minute you will have 60 predictions. 1 hour you have 3,600 predictions. You have many more things to average out. But generally speaking, that will be a better assessment, a better way of assess whether you're good or not, because we have a lot of things to average out. If you use, and the reason why now if you use a 60% raining rate for a whole year, it will be a bad measurement, is because it will actually sometimes, a lot of day actually rain, then the punishment is, a lot of day actually didn't rain, the punishment will be really big. Okay? Do people understand? So if I give you a list of prediction and what actually happened, do you guys know how to calculate the Brier score? Okay? Yes.
The Brier score is the performance score?
Is the what?
Is the Brier score the performance score?
Yeah, the performance score, yeah. It's one way of measuring the performance, right? So here you can also give it to power of 4. Then it's a different performance score. It will also serve a punishment. Just a lot of time people just use power of 2 because mathematically that's a better number to calculate. The derivative of that is continuous. That's all. Okay? Okay, so the next issue is sometimes you're assessing probability for very rare event. Okay, so like I don't know if you read this book. There's a book a few years ago called Black Swan. It's not the movie, okay? Not the who's that actress? Yeah. Not that movie, okay? Black Swan is about a rare event. It's a book actually about probability and financial market. It's actually a good book. It's written by a really good author. I really like that author. So sometimes, like for example, you're asking people to assess what's in the next year the probability of a financial crisis. That's really hard to estimate because that's not what usually happens. Okay, in the past 17 years, there was one really, 10 years actually, in the 10, 11 years. So in the 08, 09, there was a financial crisis. And this year, because of the COVID-19, there's another financial crisis now. But it's still a rare event. Not every day, so out of everyday spaces, that happens less than 100%, 1%, right? That's a rare event. So some events are even rarer. Okay, so for those events, how do you assess the probability of those? Okay, so a way to do this is we use a good friend of us, the probability tree, or here it's called event tree, but it's exactly the same thing. Okay, you basically break down the actual event you want to assess for to small pieces. For example, you know that the financial crisis doesn't happen like this. It happens because something happened first, and something happened before that, and something happened before that. Right? For example, based on this financial crisis and the past, the last one, we know that, for example, if the one big investment bank fall apart, it will cause a financial crisis. Okay, and a big investment bank fall apart is also a rare event, but we know that for a big investment bank to fall apart, it has to have something else happen first. So we do that, one by one. For example, here it is gonna assess a catastrophic failure. Okay, and for this catastrophe failure to happen, you need to have the central government, central generator overheat. You also need the secondary cooling system to fail, and then the warning system to fail. Or the warning system work, but the manual shutdown fail, and the automatic shutdown also fail. And if the warning system fail, then if the automatic shutdown doesn't work, it also fail. So these two paths can both lead to the catastrophic failure. And then, if we assume independence, we can times these probability together. So arrive at the probability here. Right? And then you add them together and get this. So the actual probability of that happening is actually 0.0000298. So if you ask people to assess that probability, I guarantee you it's not gonna be close to this number, because people are really bad at this kind of rare event. People would say something like 0.001%, and they think that's rare enough, but in reality, maybe 100 times less likely. Okay? So this is a very common event. People like to overestimate small probability and underestimate high probability. Okay? Another way to do this is use a different tree called the fault tree. But basically, this is just the reverse. So we do not, here we sort of started from the beginning, like what could cause this, that, and then to the end of the failure. Here I'm talking about, I'm asking to draw this one first. Here is the pipeline fracture. I want to know what will actually happen in the end first. And then I ask, what could cause these to happen? Here, it says that either the defective weld or the excess pressure, these two events can cause the pipeline fracture. And the or here means these two can both cause to it, as long as one of them happened. And the excess pressure is either the safety valve failure, it has to be the safety value for failure and the regular failure both happen. So it's an and then it will happen. So here, because it's an and you assume independence, so you use the times. You times these two probability, multiply these two probability together. And then you add this probability. And remember to subtract the intersected probability. This is PA plus PB minus PA intersect B. And PA intersect B is PA times PB. Okay? Understand what I'm doing, right? Because A, B are not exclusive. Okay? If A, B are exclusive, this is 0. Then you don't need to do this. Another way to do this is not the assessment method, but just changing the scale. The reason why people are really bad at probability measurement is because people are bad at small numbers. But if you transform that small number into a bigger number, or a number that people are more familiar with, then people will be fine. Okay, and to do this, we use something called the log scale. Basically, do people know this? So 10 to the power of minus 4, this is a very small number. But if you take a log, it will be, if it's a 10 base, then it will be minus 4, right? So it will become a number that people easier to understand. Easier for people to understand. In terms of these, in drawing the graph, it means this. So this is 1 over 10. This is 1 over 100. So the difference between these two is, suppose this is 1. Okay, suppose this is 1. The length of this is 1. Then this is 1 over 1,000. In actual scale, these two, the difference, and these two, the difference, this one is big, this one is small. Right? What I mean is, this is big, and this is small, right? So supposedly, if you draw a straight line like 2, 3, 4, these two are equal lengths because 3 minus 2 and 4 minus 4 are equal to each other, right? But here, you also do a 1 here. The reason is that you take a log. After you take a log, this is minus 1, this is minus 2, this is minus 3. Right? So the difference is the same. Now, this is what it means by draw a log scale graph. This is also what it means if you look at some, for example, like an economic growth graph. You will usually use a log scale. Okay, this is what it means by log scale. Okay? And do people understand why this deal with small probability? Good? Okay? Okay, so a lot of time this is the last issue. So a lot of time people need to communicate with each other about these probability assessment. Okay, so you need to talk to your boss about your assessment, or talk to your teammate about your assessment, or talk to your classmate. But you should know this. For example, people tend to prefer receiving high confidence estimate. Okay, what it means by high confidence estimate, it means people don't like to receive something like, oh, tomorrow the raining probability is 50-50. It makes people feel like you don't really know the answer. Okay, because it's the equal chance of raining or not. So it wants you to say something like, tomorrow the raining probability is 90 or is 10%. Then it means that you are very confident. So bear that in mind. And we say this a lot of time, but context affect the interpretation of probability even when they express numerically. Okay, so the same 1% in different contexts may be not the same 1%. Like I said, sometimes you would think 1% is a really large number. Sometimes you think 1% is a very small number. For example, if I told you that the probability that you'll pass this course is 1%, you will think that's really, really low, right? But if I tell you the probability that you will become a super rich person in the future is 1%, you will think that's actually pretty high, right? So that's same 1%, but you think the probability is different. I think I also mentioned this before, but if you use a frequency format, it can actually increase the imaginability of the low probability event. So what it means is, suppose you tell people that 1 out of 100 times you could die if you, sorry, that's a bad example. 1 out of, it's probably 10,000 times you would die if you take an airplane. Okay, that's maybe less than that, but just suppose that's the case, okay? That's equal to saying that, I don't even know how many zero that is, 10,000, 100,000, so 100,000, 600,000,000,001% that you could die if you take an airplane. It's the same probability, okay? But if you say it the first way, the frequency way, out of 100,000 times you could die once, people would think that's more likely to happen because people could imagine that that thing happen. Because you tell them that it actually happened out of 100,000 times. But if you tell them in terms of probability, they think that's less likely to happen. Okay? more problem about probability elicitation? Okay, so we have 10 minutes left. I want to talk about the next chapter in Hall. So let's take a break until 2:50 and come back, and then I will do a 1 hour lecture for the next chapter. Okay.